Hello students and welcome back to Chemistry B. I'm Ms. Slate and today I'm going to be working through some extra stoichiometry example problems with you. A good way to go about using this video would be to pause it when I get started and try doing it on your own, or at least as far as you can until you get stuck, and then go back and watch me work it out. The very first thing we're going to do with each and every single one of these problems is to first balance the chemical equation. So in this reaction we have aluminum oxide decomposing into aluminum metal and oxygen gas. Well, I can see that I have 3 oxygen and 2. Lowest common multiple is going to be 6. This means I have 4 aluminum in my reactants, so I need 4 in the products. Once I have the equation balanced, now I can go into the problem and figure out what is my unknown, what is it asking me to find, and what known quantities do I know about this problem. So it says how many moles of oxygen, I'm going to circle what it wants me to find, my unknown, are produced from 5 moles of aluminum oxide. So our given is 5 moles of aluminum oxide. So my unknown is I do not know how many moles of oxygen gas are produced. The first known that it gives me directly from the problem is that I know I'm starting with 5.0 moles of aluminum oxide. So what we're seeing here is we are going from moles of one substance to moles of another substance. This means we need to know what the mole ratio between them is. The mole ratio of aluminum oxide to oxygen gas is 2:3 directly from the coefficients in our balanced chemical equation. So now I can actually start to set up my problem. So I'm going to start with the given amount that I have, which is my 5.0 moles of aluminum oxide. Make sure you are always labeling everything with units and with what substance we're dealing with. I need to convert this to moles of oxygen. So I know that my moles of oxygen gas are going to go on the top, and moles of aluminum oxide on the bottom. Again, my mole ratio is 2:3 to aluminum oxide to 3 moles of oxygen. My moles of aluminum oxide cancel, and I'm left with moles of O2, which that was the unknown that I wanted. So I don't need to go any farther with this problem. I just need to compute it. So I'm going to do 5 times 3 divided by 2 gives me 7.5. Now, next thing we have to do is we have to look at sig figs. If we go back to our original amount, our original starting amount has 2 sig figs, which means that's how many our final answer should have, which indeed in this case it does. So no rounding is required. I can just write my units and my substance, oxygen gas. Let's try another one similar to this that is using the same chemical equation. How many moles of aluminum oxide are required to produce 2.5 moles of aluminum? Well, again, how many moles of aluminum oxide, that's what I want to find, that's my unknown, are required to produce 2.5 moles of aluminum? That's one of my knowns. So my unknown, what I need to find is moles of aluminum oxide. one of my knowns is that 2.5 moles of aluminum are being produced. Again, this is a problem where we're going from moles of one substance to moles of another. To convert from moles of one substance to moles of another, we need to use their mole ratio from the chemical equation. In this case, the mole ratio of aluminum oxide to aluminum is 2 to 4. Alternatively, you could reduce that and make it 1 to 2. Either way will work for the problem. In this case, I'll use the mole ratio exactly from the chemical equation without reducing. But again, sometimes reducing can save you a little bit of work. But either way will work. So I'm going to start this the same way I did before with my first known quantity, 2.5 moles of aluminum. I want to convert that to aluminum oxide. So moles of aluminum oxide will go on the top, and moles of aluminum on the bottom. And again, this is a 2 to 4 or 1 to 2 mole ratio. My moles of aluminum cancel, and I'm left with moles of aluminum oxide. That was my unknown. No further work is required for this one. Now I just need to compute. Again, you could multiply 2.5 by 2 and then divide by 4, or just divide it by 2. And you get 1.25. However, we have to go back to our original starting amount for sig figs. There are 2 significant figures in 2.5, so I am going to need to round my answer. It should come out to 1.3 moles of aluminum oxide. So those are some examples how to do some basic moles of one substance to moles of another problems. Let's look at our next example. Now let's look at question 2. Copper 2 oxide reacts with sulfuric acid to produce copper 2 sulfate and water. First thing we're going to do is we are going to balance the chemical equation. So I've got 1 copper, 1 copper, 1 sulfate, 1 sulfate, 1 oxygen, and 2 hydrogen. Everything here is balanced. They're all going to have a coefficient of 1 in front of them. Our first question says, how many molecules of water are produced when 0.75 from 0.75 moles of sulfuric acid? Well, first off, let's jot down what our unknown and knowns are. So our unknown in this case is molecules of water. And our first known is 0.75 moles of sulfuric acid. And if we're looking at this, okay, we're starting with moles of our acid and we want molecules of water. So that means we're going to have to go from moles of acid to moles of water and then convert from moles of water to molecules. So this is going to be a 2-step process here. So if I want to go from moles of one substance to moles of another, I need to use the mole ratio. Luckily in this problem, since the equation was already balanced, all of our mole ratios are just 1 to 1. That'll make the math easy for us. Lastly, to convert between moles and molecules, we need to use Avogadro's number, which tells us that 1 mole is equal to 6.022 times 10 to the 23rd molecules, or really any particle for that matter. Now that I've outlined my unknown and my knowns, I can set up my calculation here. So I'm going to start with my first known, 0.75 moles of sulfuric acid. I need to convert from moles of sulfuric acid to moles of water. Lucky for us, our mole ratio is just 1 to 1. Now that I have moles of water, I need to use Avogadro's number, to figure out molecules. Now I am left with units of molecules of water. So now I can do the calculations in my final answer. Since our mole ratio is just 1 to 1, we're going to multiply 0.75 by Avogadro's number. Now, when you're doing problems with Avogadro's number in your calculator, you need to be very careful with how you input it. There's a couple of ways to do this. Number one is to use parentheses. So you could go 0.75 times parentheses 6.022 times 10 raised to the 23rd. And that'll give you the correct answer. A slightly simpler way to do it, especially if you have a scientific calculator like mine, is to go 0.75 times 6.022 and then hit second and the E button right here. That E is your times 10 to some power. Then I just type in my exponent, 23. Now I no longer need parentheses to get the correct answer. So when you're computing things where you've got numbers in scientific notation, make sure you're either putting everything in parentheses or you're using the E button. Otherwise, you're likely going to have a calculator error. So when we do this, our final answer becomes 4.5165 times 10 to the 23rd. Now we need to round to sig figs. Our original number, 0.75, has two significant figures in it. So I need to round my answer. So my final answer becomes 4.5 times 10 to the 23rd molecules of water. Now let's look at part C here, which this is going to take us a little bit farther, but we're still going to be working with molecules. It says how many molecules of copper 2 oxide, really should be formula units of copper 2 oxide, but it'll work for our purposes, are required to produce 1.204 times 10 to the 23rd molecules of water. Well, first off, let's mark our unknown. Our unknown in this case is molecules of copper 2 oxide. Our first known is 1.204 times 10 to the 23rd molecules of water. Now looking at this, I am starting with molecules of water, and I want to get to copper 2 oxide molecules. So I'm going to have to convert from molecules of water to moles of water, then to from moles of water to moles of copper 2 oxide, and then lastly, again at the end, then I'll be able to convert from moles of copper 2 oxide back to molecules of copper 2 oxide. So this is a little bit longer. This is a 3-step process, but we set it up the exact same way. We still need to know our mole ratio, which again in this problem for everything is 1 to 1. And we still need to know Avogadro's number. 1 mole equals 6.022 times 10 to the 23rd molecules. Now we can set up our calculation, starting with our 1.204 times 10 to the 23rd molecules of water. We're going to use Avogadro's number to convert that to moles. And now that we have moles of water, we can use our mole ratio to convert to moles of copper 2 oxide. And lastly, we're going to use Avogadro's number again to convert finally to molecules of copper 2 oxide. Now, we could go through, divide by Avogadro's number, multiply by 1, multiply by Avogadro's number again, or you could look closely here and notice a little shortcut. First off, our mole ratio is 1 to 1, so we can essentially ignore it. It's not going to change our number. But also, we are dividing by Avogadro's number, and we are multiplying by it. If you divide something by itself, you get the number 1. So essentially, Avogadro's number cancels itself out on both sides in this equation, which means our number of molecules of water that we started with is going to be the same as our molecules of copper 2 oxide that we end with. Our final answer is going to be 1.204 times 10 to the 23rd molecules of copper 2 oxide. And this should make sense based on our chemical equation. If one molecule of copper 2 oxide can combine with one of sulfuric acid to make one water and one copper sulfate, then our total number of molecules should never change beginning and end. So that's why this answer makes sense. Again, the very first thing that I'm going to do is I'm going to balance the chemical equation. So here we've got potassium metal reacts with nitrogen gas to produce potassium nitrate. Well, I've got 1 and I've got 3 and I've got 2 and 1. So I know I'm going to need a coefficient of 2 right here. And that means I now have 6 potassium over here. So I'm going to need a coefficient of 6 there. And again, leaving this blank, that's the same as saying we've got a coefficient of 1 right there. Next, we're going to look at our equation. What mass of potassium is required to completely react with 1.25 moles of nitrogen? So remember, we're starting with moles of one substance, and we want mass of another. So we're going to have to go from moles of one substance to moles of another, and then convert back to mass. Our unknown in this problem, what we want to find, is our mass in grams of potassium, and we want to, what our known is 1.25 moles of nitrogen, nitrogen gas, N2 to be specific. Well, one of the things we know, if we've got to go from moles of one substance to moles of another, we need to know the mole ratio. So let's look at our balanced chemical equation. Our mole ratio of potassium to nitrogen is 6 to 1. And then notice we're going to have to go from, because we're going from moles of nitrogen gas to moles of potassium to mass of potassium. Anytime we have to convert from moles to mass, we need to know the molar mass of the substance. So this is where our periodic table comes in, which I happen to have one handy. It may not be the same one that you're using. Just remember that if you're using a different periodic table than me, or you're using molar masses out to different decimal places than me, you might get a slightly different answer. If your answer only differs from mine by a few tenths, that's fine. In most cases, you'll never be marked down for a difference in rounding. In AP chemistry, or when you go to college and take chemistry there, professors are usually very specific with how many decimal places they want you to use in your molar mass. So if I'm going from moles of potassium to mass of potassium, I need the molar mass of potassium. So 1 mole of potassium has a mass of, pull out our periodic table, here's potassium. I'm going to use molar masses to just 3 decimal places because typically you don't need anything more than that unless you're doing really, really precise work. So that would make it 39.1 grams is the mass of 1 mole of potassium. So now that I have all my knowns and I know what I'm trying to get to, I can set up my actual calculation. Again, starting with what I was first given, my first known, 1.25 moles of nitrogen. Again, I know I need to get to potassium. Our mole ratio of potassium to nitrogen is 6 moles of potassium to 1 mole of nitrogen gas. Moles of nitrogen cancel. Now remember, my unknown is my mass in grams of potassium. So again, I'm going to need to use molar mass. I know that 1 mole of potassium has a mass of 39.1 grams. And now I have mass of potassium as my final units. That's what I want. Now it's time to do some calculating. So I'm just going to take 1.25 times 6 times 39.1, and we get 293.25. But again, we need to round to the appropriate number of sig figs. Our original starting amount has 3 significant figures, so we need to round our final one to just 3 significant figures. So our final answer becomes 293 grams of potassium. All right, now let's look at our next problem. This one says, what mass of nitrogen is required to produce 25 grams of potassium nitride? So here, what we have going on is we're starting with our mass of potassium nitride, and we need to get mass of nitrogen. Well, again, if we're going from one substance to another, we got to convert to moles. So we're going to need to convert from mass to moles of potassium nitride, and then to moles of nitrogen, but it wants mass, so at the end we need to again convert from moles to mass. So here we've got, we're adding one extra calculation. So we started with one conversion, we added on a second one, now we're up to 3 conversions here that we need to do. So let's again kind of sort out what our knowns and unknowns are. So first off, our unknown is our mass of nitrogen. So that's going to be grams of nitrogen gas. Some of our knowns. Well, first off, we are given that 25 grams of potassium nitride is being produced. If we want to convert from mass of potassium nitride to moles, we need to know its molar mass. We need to determine what 1 mole of potassium nitride's mass is. Well, that's going to require us to add 3 times the mass of potassium to 1 of the molar mass of nitrogen. So if we look this up here, again, potassium is going to be 39.1. And I'm going to need to multiply that by 3. And add it to the mass of nitrogen, which is like 14.0. So this is the math that I'm doing roughly to figure out what the molar mass is. And we get that 1 mole of potassium nitride is equal to 131.3 grams. Okay, that's what we need to know to go from mass of potassium nitride to moles. To go from moles of potassium nitride to moles of nitrogen, we need the mole ratio. Well, that comes straight from our balanced chemical equation. The ratio of nitrogen to potassium nitride is 1 to 2. And then lastly, we need to be able to convert from moles of nitrogen gas to mass. So we need the molar mass of nitrogen gas, not just nitrogen. Remember, nitrogen gas is a diatomic molecule, so we're going to have to double the molar mass of nitrogen. So doubling 14.0 gives us a molar mass of 28.0. So 1 mole of nitrogen gas has a mass of 28.0 grams. Now we've sorted out what all of our conversion factors are going to be. Now we can set up our calculation. So again, I'm going to start with what they gave me, 25 grams of potassium nitride. The first thing I need to do is convert this to moles of potassium nitride, which we found the molar mass to be 131.3 grams. Now that I have moles of potassium nitride, I can now convert to moles of nitrogen gas, where we said the mole ratio of nitrogen to potassium nitride was 1 mole of nitrogen gas to 2 moles of potassium nitride. Now I have moles of nitrogen, but remember, my unknown is mass of nitrogen. So again, I need to do one more conversion. We said the molar mass of nitrogen gas was 28.0 grams in 1 mole. Now I'm left with just mass of nitrogen. So now I can do my calculating. So I'm going to take 25 and I'm going to divide that by 131.3. And I'm going to divide that answer by 2. And then lastly, I'm going to multiply by 28. And we get an answer of 2.6656, etc., etc. We need to round to significant figures. If we go back to our first given value, 25 grams, that has 2 significant figures. So we need to round our final answer to just 2 significant figures, which in this case means our final answer is going to be 2.7 grams of nitrogen gas. And that's how you do a full mass-to-mass stoichiometry problem. We've got a few more problems to go through. These ones are going to focus on mixed stoichiometry conversions. So number 4 here, we have copper 2 oxide reacting with hydrogen gas to form copper metal and water. Again, the very first thing I'm going to do is balance the chemical equation. So I've got copper, copper, oxygen, oxygen, 2 hydrogen, 2 hydrogen. Lucky for us, it's already balanced. I picked equations that would be easy to balance on this worksheet so that we wouldn't have to spend a lot of time on that aspect of it. Because what we really want to focus on here is the Stoich calculations. If we look at our question, it says, what mass of copper 2 oxide is required to produce 3.7 times 10 to the 23rd molecules of water? So we are starting with molecules of water. Eventually we want mass of copper 2 oxide. Well, again, if we have to convert between quantities of 2 different substances, we need to go through moles first. So I'm going to have to convert to moles of water. Then I'll be able to convert to moles of copper 2 oxide. We want mass, so at the end we're going to have to convert back to mass of copper 2 oxide. So again, another process that's going to require like 3 different conversions. But let's start that process by just kind of looking at what our knowns and unknowns are going to be. So the unknown that we're really looking for is our mass in grams of copper 2 oxide. The things that we know that are knowns. First off, we know that we're starting with 3.7 times 10 to the 23rd molecules of water. Well, one of our first calculations is going to have to be molecules to moles. To convert between moles and molecules, we need Avogadro's number. So that is where 1 mole is equal to 6.022 times 10 to the 23rd molecules. Then we need to convert from moles of water to moles of copper 2 oxide. That requires us to use the mole ratio. Luckily for us, everything in this equation has a mole ratio of 1:1. Lastly, we need to take our moles of copper 2 oxide and convert it to mass in grams of copper 2 oxide. Anytime we're converting between moles and mass, we need to use the molar mass. So we need to figure out, using the periodic table, what mass in grams 1 mole of copper 2 oxide is equal to. Well, again, I'm just going to need to take the molar mass of copper and add it to the molar mass of oxygen. In this case, copper has a molar mass of about 63.5, and oxygen has a molar mass of about 16. So that gives us 1 mole of copper 2 oxide has a mass of 79.5 grams. Now that we know all of our conversion factors, now we can set up the calculation. Starting with our first known, 3.7 times 10 to the 23rd molecules of water. We're going to use Avogadro's number to convert that to moles first. 1 mole, there are 6.022 times 10 to the 23rd molecules. Molecules of water cancel. Now that we have moles of water, we can use the mole ratio to convert to moles of copper 2 oxide, which again, the mole ratio for this equation is 1:1 for everything. Lastly, we need to multiply by the molar mass of copper 2 oxide. So we know that there are 79.5 grams in 1 mole of copper 2 oxide. Now that all of this is set up, now we can do our calculations. So first off, I'm going to take 3.7 times 10 to the 23rd, divide it by Avogadro's number. Remember using the E button in your calculator or putting everything in parentheses. Once you've done that, we can just multiply by molar mass because our mole ratio is 1. So multiply by 79.5, and we get a final answer of 48.845 ... Significant figure time. Our starting number has just 2 significant figures, the 3 and the 7. So we need to round our final answer to 2 significant figures. So that means our final answer is going to be 49 grams of copper 2 oxide. Let's look at our next mixed stoichiometry problem. Again, we have antimony reacting with water to form antimony 3 oxide and hydrogen gas. First thing I'm going to do is balance the chemical equation. So I've got 1 and 2 antimony. I've got 2 hydrogen and 2, and I've got 3 oxygen and 3. Well, to make it 3 oxygen, I can just put a 3 there. Make it 2 antimony, I can put a 2 there. This now means I have 6 hydrogen, so I can put a 3 there, and everything should be balanced now. Let's look at the question. It says, how many liters of hydrogen are produced from 103.0 grams of antimony. Well, let's identify some knowns and unknowns here. So our unknown is our liters of hydrogen gas. Liters is a unit of volume. We're going to have to use molar volume here. For any of these problems that require you to use molar volume, we can assume that we're dealing with ideal gases at standard temperature and pressure, because that's the only way we can solve these problems at this point. Next, let's do our knowns. Our first known is the 103.0 grams of antimony. So if we're kind of looking at this problem a little bit, we're going to need to go from our mass of antimony to moles, because again, if we're converting between two different substances, we need to go through moles. Once we have moles of antimony, we can then use the molar ratio to convert to moles of hydrogen gas. Our unknown, though, is liters of hydrogen. So we then, at the end, need to convert to our volume of hydrogen gas. Well, the first step of that is converting from mass to moles. So we need to know the molar mass of antimony, which if we look on the periodic table, 1 mole of antimony, element number 51, is about 123 grams. To convert from moles of antimony to moles of hydrogen, we need to know the mole ratio. If we look at our chemical equation, our mole ratio of antimony to hydrogen is 2 to 3. Lastly, we need to be able to convert from moles of hydrogen to volume. Well, this is where we're going to need to use our molar volume conversion factor. Again, remember, for these problems, we can assume that we're dealing with ideal gases at standard temperature and pressure, which for ideal gases at standard temperature and pressure, we know that 1 mole of a gas is equal to 22.4 liters. Now that we kind of have all of our conversion factors and our process mapped out, we can then go about setting up our calculations. Starting with our first known, 103.0 grams of antimony. Converting that to moles of antimony using the molar mass, which is about 123 grams. Now we can use our mole ratio to convert from moles of antimony to moles of hydrogen gas. Now we have moles of hydrogen gas, so the last thing is we need to use our molar volume to convert to our volume, our liters of hydrogen gas. Now we have our final units of liters of hydrogen. That's our unknown. Now we can see about doing our calculations. So first I'm going to take 103 divided by 123, and that number times 3, and then divided by 2, because that's how our mole ratio works. And then lastly multiplied by 22.4. And we get a final answer of 28.136 ... Again, we need to round to sig figs. If we look at our starting value, this has 4 significant figures. Remember, if the 0 comes right after a decimal place, it is indeed significant. So 1, 2, 3, 4 means that I then need to round my final answer to 28.14 liters of hydrogen gas. Let's do one more mixed stoichiometry problem together here. So start again by balancing the chemical equation. So I've got 1 copper, 1 carbon, 1 carbon, 3 oxygen, 1 plus 2 for 3 oxygen. Again, this equation is already balanced. I've been picking easy ones so that we don't spend our time on the balancing. This problem says, what mass of copper 2 carbonate is required to produce 55.0 liters of carbon dioxide? Well, this means my unknown is my mass in grams of copper 2 carbonate, and my first known is 55.0 liters of carbon dioxide. All right, so if we think about this on the roadmap, how we have to go, we are starting with a volume of carbon dioxide. We need to eventually get to mass of copper 2 carbonate. Again, converting from one substance to another, we must go through moles. So first I'm going to have to convert to moles of carbon dioxide. Then I'll be able to convert that to moles of copper 2 carbonate. And then lastly, we'll be able to convert to our mass of copper 2 carbonate. Well, first off, if I need to convert between volume and moles, that's where my molar volume comes in. I know 1 mole of an ideal gas at standard temperature and pressure has a volume of 22.4 liters. To convert from moles of carbon dioxide to moles of copper carbonate, that requires our mole ratio, which fortunately for us in this problem is 1:1 for everything. And lastly, we need to convert from moles of copper 2 carbonate to mass. To convert from moles to mass, we need to use our molar mass. So we need to determine what the mass of 1 mole of copper 2 carbonate is. So that's just going to require us to add up the molar mass of copper, carbon, and 3 times the mass of oxygen. So if you look at your periodic table, copper has a molar mass of about 63.5 plus the molar mass of carbon, which is about 12.0, plus 3 times the mass of oxygen, which is about 16.0. That gives us a molar mass of 123.5 grams. Now that I have my roadmap marked out, I have all my knowns and unknown written down, let's set up the equation. Starting with my first known, my 55.0 liters of carbon dioxide. Need to convert that to moles using molar volume, where 1 mole of an ideal gas at STP is equal to 22.4 liters. Now I can go from moles of carbon dioxide to moles of copper 2 carbonate using our mole ratio, which is 1:1 in this problem. Lastly, we need to convert from moles of copper 2 carbonate to grams using our molar mass, which is 1 mole is equal to 123.5 grams of copper 2 carbonate. Now I'm left with grams of copper 2 carbonate as my final unit. Let's do some calculating. 55 divided by 22.4, and then just multiplying by 1's the same, so then multiply by 123.5. And we get 303.236, etc. Let's go back to significant figures. 55.0 has 3 significant figures. Again, if the 0 comes after a decimal place, it is significant. So 1, 2, 3 sig figs. My answer should round to 303 grams of copper 2 carbonate. I hope this was helpful. Again, feel free to email or drop into office hours with any other questions that you have. Take care, and I'll catch you next time.